This is take three on recording because I haven't been able to successfully record this. And welcome to my presentation of my semester project for one of my classes here. We're doing a Cartesian robot. Cartesian robots basically pick stuff up. Think of them like Amazon robots. They pick up objects and move it. And this class is a very open class and basically gives you a problem and says solve it. And use MATLAB and Simulink to solve it. And if you have any questions, just come to the class and ask questions. So it's a very open-ended class, and we managed to get the robot kind of working. And we wanted to we had a few priorities for ourselves. So my personal priority was if you're going to give me this kind of project, I wanted to be able to build it in real world. So I didn't want to build, I guess you would say, a hypothetical machine. I wanted to know that we could build it, and I wanted it to be cheap and using reproducible parts. I believe the Cartesian robot we build can be built with about 250 euros. The objects we're going to use is 5 stepper motors for a total cost of 40 euros. Arduino. The Arduino is going to be handling the PID control as well as serving as a master base for calculations and position sending. We need sensors for position control, so I decided to use the only ones that I think I had a chance of understanding, which would be this one right here. So this one does a position detector for auto leveling, so it does Z detection on position, but I actually think that we can use this for X and Y as well. Finally, we have for position detection of objects in our field of view, machine object detection is probably the best. We've seen it used before. And this camera with the ESP12 camera, I think, is the best one. They're cheap, like 2 euros each. No wonder everyone likes object detection. So, I put 40 here, but it's finally the joints and the casing which we would need, and the aluminum profile bars. That was 30 euros. So I think 200 euros, 250 euros is all you would need. So we did a lot of research on how these machines work. Obviously, we come from different backgrounds. We looked at the CAD models. A couple of things stood out to us. Um, we're going to separate this into three elements. So the three elements we're going to discuss is the plant, the stepper motor, and the controller, and how we put this all under control. You can see that this looks like a PID control system because it used to be. We had the PID control and the transfer function would have gone, the transfer function was used to be here and it used to be here. You'll see why we took it out, but we did have it under PID control uh, in Simulink. Uh, the real world obviously is a little more complicated in that way. So let's go step one. Let's look at our plant. So this is our plant in Simulink. It used to be much more complicated. We simplified it, and I will show it here on SolidWorks. It has three joints of it moves across the X and the Y plane. So let me float these around a little bit so I can play. So it moves on the X and Y here, and it moves up and down. Each of these has been carefully modeled. The only parts that we would need to build custom job is the brackets that hold the rods and the carts themselves, which are relatively simple aluminum jobs. Uh, the last part that's not in the model that you're seeing here is that we need threaded rods. We would do rack and pinion to move these objects, and so we have a base model here that normally attaches to this, and the threads turn the rack and pinion. We would use an M5 rod to do this. And then, yeah, and then finally, this stepper motor here doesn't have, the stepper motors used to be in our machine. I actually have CAD models of the stepper motors that we would use. I took them out because they were killing my computer, but a stepper motor pulls two M5 rods for the X plane, a stepper motor rotates the Y plane rod, and then finally a stepper motor is sitting on top of this machine that contains the pincer. It sits on top and it moves two sets of rack and pinion to successfully move the machine up and down. the main considerations now, this is removing a 1 kilogram object, so these stepper motors don't need to be too strong. The only one that needs to be strong is the one that holds the Z-plane, because it needs to produce enough holding torque to hold against this object falling. The holding torque that we decided on was the 1 kilogram, so you have basically 10 newtons of force being worked on the machine. Uh, and to lift that, you would need about 20 newton meters. 20 newton centimeters. And so as long as you had a 40 newton centimeter just as a buffer, we felt like that was enough. So yeah, and it's moved all by stepper motors. Stepper motors are fun little things. They give you precise control, and they convert rotational motion of a DC motor into different steps, which allows you for higher precision control. These motors revolve extremely fast. You can find them online, and they are extremely pivotal for any type of drones that fly, RC cars, and obviously for 3D printers, they're incredibly clutch. Pun intended. That was a pun. No one's gonna understand this pun. Anyways, so we are so here we are as the plant. We can look at the actuation of the stepper motors. So the stepper motors are running here. We have it's very interesting. So we have a stepper motor driver. So the stepper motor drivers are providing us the parameter blocks in Simulink to be able to set the requirements. Now in this stepper motor driver, we only had 10 volts. Uh, we think that the objects itself probably can do with 5, but I would assume a 12-volt system should be enough. 10 is what we modeled. 12 is good. 5 is minimum, is what I'm trying to say. What we like about this driver module that we picked up from Simulink is that it gives us position control. And this is why I don't have PID control. If we have overshoot, which we can, someone could hit the table and we definitely would have overshoot. There's no way that these objects can move without moving the threads. And because of this, it's impossible. The position control drivers of the stepper motor will cause the overshoot to be corrected. You just have to watch out for oscillation. The oscillation, there's a lot of resonance problems in stepper motors, and so you need microsteps. So basically, each single 1.8 degree turn of a stepper motor needs to correspond to 4 position steps of the stepper motor in order for the impact to take place. And so we do this by adding microsteps, and this helps bring down a lot of that oscillation that can mess up some of these systems. So that helps us with precision. Finally, controllers. This is basically the job of translating the input signals from our machines. We get a Cartesian plane, and so we need to translate these into the position steps. And that's the beauty of a driver for stepper motors, is that I don't need to send commands to my stepper motors to do, to hold a certain time of velocity. I'm actually just holding positions. Hence why the PID control has been removed. But if I had had a speed or a command to hold a certain velocity on I would probably add it. And you would add it so by adding the transfer function right here, and then the PID control here, right here. But thankfully, not our problem today. So this is a simple model. We're going to show it move now. We're going to move it. So here is one of the first two jobs combined. So you can see that the object is placed right here, and you're going to see the object, our object, detect its position and open up its pincers and get into the appropriate latching position for the object. One of the key elements to note is obviously I don't have a lot of time. I got kids, literally I got kids to feed, I got a job, and so the kind of the next steps here is to segment the work done by the lever and the actuation into different jobs. So for example, right now you can see that the what do you call it? The lever opens up at this stage, but it could be better if we had the lever stepper motor opening up at a high rate. So right now, this is a one job because we did not create like a simulation time. But the next step here is to program this object to lift, return to home, which is a high position, find the objects in the X and Y plane and lower and then grab. But essentially, these are all the jobs in one. Uh, so how do you make sure you picked up the object? Well, the ESP cameras that we discussed can make sure that the object is the center of mass is moving. Having object detection is useful because I can identify the object being moved and I can identify the uh, the center of mass of the object, which is the most critical element. The other components to consideration, the other considerations to have is to control that to make sure the object could come in. So I'll describe this in simplest terms: better, good, better, and best. So good would be to have the ESP12 cameras constantly monitoring the object, so you can see how the object is behaving under the external force of our machine. Better, you could do this and you could have a scale, and the scale should be able to measure the total weight of our system. So if our total net weight of our system is proportional to what we expect it to lift, then we're in the grabbing of the object. And best is to, well, and that is those are the two of the best ones right there. So yeah, and so you kind of identify the object that way. Yeah, that's all there is to it. So this is how we got in the project, and it was obviously a lot of fun for me, but it was an intense amount of work. It was not easy. Uh, the full assembly is got well over 40, 50 parts. You can see we've even threaded every single hole. We know this machine. I know this machine like the back of my hand, and I could build this machine. Uh, yeah. But anyways, thank you very much for your time and have a good day.